Welcome to our lecture number 4. And today we are going to speak about magnetostatic waves, or they are also named dipolar spin waves. This is one of the important lectures, and because spin waves which are investigated nowadays are mainly this type of waves, dipolar spin waves. So what we will discuss here, we will go first through magnetostatic approximation. What is that? And we will get a Walker's equation. And then we will discuss 3 main types of the waves, which we have seen already in the introductory lecture. It's forward volume magnetostatic wave, it's backward volume magnetostatic wave, and magnetostatic surface wave, also called Damon-Eshbach mode. So what is magnetostatic equations and what is Walker's equation? This is a dispersion which you have seen already, so and our job is now to understand how to get these dispersion curves for forward volume, backward volume magnetostatic wave, and to see how we can tune parameters of this wave. That's very important. One of the advantages of spin waves is that you have many parameters how you can change these dispersion curves. So that's the same curve with in logarithmic scale. So now today we are focused on this part, dipolar spin waves. So dipolar exchange spin waves we don't discuss, or maybe we will discuss only when we will go to confined structures a bit, but principally here you just need to take into account both dipolar and exchange. Exchange we already took last time, now we are talking about this magnetostatics. And first, what we need to take into account that here, in addition to dispersion of spin waves, we will have also dispersion for electromagnetic wave. This one. And it's very different. And if you go to the frequencies in gigahertz range, like it's shown here, dispersion, this is not calculated, this is just here placed as approximately. And first what we see comparing dispersion for spin waves and for electromagnetic is that electromagnetic has very short wavelengths, a very small k, which means that it has large wavelengths. So for 10 gigahertz, the wavelengths of electromagnetic wave in air should be 3 centimeters. Yeah? So it's centimeter long wavelengths, centimeter kind of wavelengths of electromagnetic waves. So if you will go to our lab and you will see take some attenuator, the size of waveguide scales with the size. So if you have attenuator for 4 gigahertz, it should have such a big waveguide. Yeah, so it means that wavelength is larger. Then if you go to 10 gigahertz, it's getting smaller and so on. Therefore, but wavelengths of spin waves can go also from centimeter principally here, but down to microns, even in this range. Therefore, what we see is that spin waves have much shorter wavelengths for the same frequencies. That's first. And second, we discussed that group velocity of any wave is defined as a slope of dispersion curve. So here it was negative, if you remember, here it's positive, but you see how steep is electromagnetic wave. And its dispersion is simply omega divided by c, and it's simply and dispersion curve is huge. Dispersion velocity is speed of light simply. Yeah, if it's light, and spin waves have very steep slope. So it means that spin waves are much slower compared to electromagnetic wave or to light. Good. And why it's important? Because that's exactly what is staying behind the term magnetostatic approximation. And this wave obtained in the magnetostatic approximation is named magnetostatic wave. And it sounds very weird because wave by definition is dynamic object which moves. Yeah? And here we're discussing static wave. And this static is coming from the fact that simply our waves are much slower compared to light. That's why magnetostatic approximation. So how to define magnetostatic approximation? So usually people compare k, because the speed, it also relates to the wave number. And they say that wave number, so waves or eigenexcitation in your magnetic media, which have larger k compared to k of electromagnetic wave, is when this one is satisfied, then you are working in so-called magnetostatic approximation. And here n is refractive index, yeah, and but usually refractive index is used for optics, for transparent media. It cannot be very large, but if you go speak about electromagnetic waves, when you go to some special ceramics, this epsilon, so it's not transparent, but electromagnetic wave propagates, and this n can be much larger. But then we usually operate with so-called dielectric constant eta, epsilon, and n is equal simply square root of epsilon. And so this is our magnetostatic approximation. Let us see where it is located. How large should be our K? Example, yttrium iron garnet, epsilon 10, square root is 3, speed of light, frequency, let's take 10 gigahertz. So it means that your K should be more than 6 radian per centimeter, or much more than 6 radian per centimeter, and then you can deal with magnetostatic approximation. And here we have a fun situation, because this region of spin waves is named magnetostatic waves. And the requirement is simply that K is larger than this value that we go to the side. And these waves are called spin waves. But in reality, both of them are called spin waves. This also are named spin waves. And both of them are magnetostatic waves. Moreover, this exchange spin waves, for it, because it has so large K, the magnetostatic approximation is satisfied even better. So exchange waves principally is even more magnetostatic than this one. But in terminology, it happens that people do not name this one magnetostatic, and they introduced another border, how to define it. From left side, it should be larger than K electromagnetic, but from another side, it should be still the role of exchange interaction. Exchange energy should be small. So it means that this is magnetostatic and dipolar wave, so no exchange interaction. How to define this right border? There are different ways, but for example, this one is often used when they take delta H, it's a ferromagnetic resonance line width, they divided it by exchange constant D. And for exchange, for spin waves, for YIG, these are typical parameters, then you will get 10 to the power of 4. Yeah, and wavelength with 2 pi divided by 10 to the power of 4. So principally, it should be in somewhere in micrometer range. So it means the following, that magnetostatic waves, that we are not confused. Here's our 10 to the power 4. It's something which goes from 10 radian per centimeter till 10 to the power 4 approximately. For YIG, yeah, it can be different for different materials. Another way, just very simplest approximation, is that if wavelength is larger than 1 micron, then it's most likely magnetostatic wave. When it's smaller than 1 micron, then exchange should be taken into account. Is this point clear? No confusion? Okay. Good. Maxwell equations. So we all know Maxwell equations, and so there are 4, and principally they describe everything. In classical world, they don't describe exchange business. How it is applicable to the case of magnonics. Maxwell equations describe magnetostatic waves. So principally, this is more or less electromagnetic wave propagating in a magnetic medium. Maxwell equations do not describe exchange interactions, therefore you cannot describe exchange spin waves with Maxwell. But today we are focused on magnetostatics, and what is our Maxwell equations are telling us. So the first one, so here you have it in SI and CGS system, again, that you are not confused. And the first one is telling the divergence of displacement field D is equal to rho. So more or less Gauss law of electricity, which says that if you have a charge in your system, there will be electric field also. Second one is a Gauss law of magnetism, which shows the divergence B this magnetic inductance or magnetic field B will be 0. It means that our magnetic line should be always closed, which is a fundamental, which gives us fundamental outcome that there are no magnetic monopoles. Yeah, that whatever you have in the system, there will be always dipole. If you cut it in the middle, there will be again dipole and dipole. The next one is rotor E is equal minus dB over dt. It's Faraday's law of induction, which means that if you change field, so it's not constant, there is variation of the applied magnetic field or magnetic induction B, there will be electric current in such circular form. And the last one gives us, so here two laws, principally Ampere's law, that tells us if you have current in your system J, then there will be Ørsted field around. And if you change electric displacement field D in time, you will also create circular field around. And this is more or less staying behind the electromagnetic wave, how it propagates in vacuum. So that's our Maxwell equation. And why it's important? Because in the case of magnetostatic approximation, we can simplify it. And the simplification is principally this term, that dd over dt is equal to 0. So it means that this displacement field d is slow compared to, so our variation is very slow compared to electromagnetic wave. That's why this variation can be taken as a 0. Moreover, in practical cases, like for example for yttrium and garnet, it's isolator, you cannot send current through it, therefore you can say that current is equal to 0, like it's shown here. Therefore this is 0, and then you are getting Maxwell equations in the magnetostatic approximation, which tells us that rotor H is equal 0, divergence B is equal 0. Or B you can rewrite via magnetic permeability tensor mu times magnetic field H. And that's what we need in order to be able to get dispersion curves for magnetostatic waves. How do we do it? And here, although I just said that there are no magnetic monopoles, but in magnetostatic approximation, when rotor H is equal 0, you can introduce such value as magnetostatic potential phi. And this magnetostatic psi, sorry, yes, I misprint. And this one can be introduced in a way that gradient of psi is equal to field H. So you artificially introduce such parameter of the magnetostatic potential and you immediately couple it to the field. Why it's interesting? Because then we are coming back to this equation, divergence B is equal to divergence mu tensor then H, which you rewrite in terms of gradient of psi, and that's what you can have. And this is principally your generalized Walker equation, because divergence B, as we discussed, is equal 0, yeah? So here should be equal 0 staying. So this is our Walker equations. But that's not the form in which he has written it at the very beginning. We can simplify it. For this, what we do, we take a permeability tensor, which we defined in the first lecture, a second lecture, and we discussed FMR and pull the tensor. And then we had this mu A, antisymmetric, and this is mu A, it depends on mu omega H, which is defined by the field. It depends on omega M, which is defined by M0 for SI units of system and CGS. So CGS is in blue. If you see 4 pi, then it means it's CGS. If you see mu0, it means that this is SI. Good, then what you do, you just take gradient of psi, yeah, it's just such vector, d psi over dx, d psi over dy, d psi over dz. And if you multiply it with this tensor, you will get this, this vector. Then what we do next, we just take this vector and plug it in this equation. So we more or less need to find a divergence, which is dx component over dx plus dy component over dy and plus dz component dz, and that's what we're obtaining. So you can immediately see that this first term, d2 psi over dx squared, is coming from here. When you differentiate over x, the second term is coming from second derivative over y from here, and mu is staying in front. This two disappears because they are the same, but after differentiation, this one over dx and this one over dy, but they have different sign. And you still have the third term, which is simply differentiation, this one. And this is a Walker equation, how it was originally written by Walker. And that's what gives us a possibility to get dispersion of magnetostatic spin wave. Other questions to this point? No? All is clear? Yes. Again, a few words about terminology. So classical terminology. So now we are jumping to one concrete case of wave, forward volume magnetostatic wave. You see, I have this word spin because in classical MSW, this MSW means magnetostatic wave. This is M, this is S for static, and this is W. Nowadays, terminology slightly changes. People want to underline that this is a spin wave. Therefore, often this is magnetostatic spin wave. And then this is for M, this is for S, and this is for W. Therefore, just don't be confused in terminology, as both can be used. And forward volume, it's a magnetostatic MSW, which is propagates in the out-of-plane magnetized thin film. That's our thin film. And here is a sketch, because now we will have to solve equations, and what we are going to do now, it's very similar to that what you did already in quantum mechanics when you described electron in potential well. A very similar approach. What you need to do, you need to have defined your equation in each region, and you need to use boundary conditions. Strictly speaking, all this mathematics is not complicated, but it's very bulky. And if you plan to do PhD in your PhD in Magnonics, so I would recommend to go through this mathematics once in your life, just that you feel how it works, that you know where this dispersion comes from. And here I will just show you steps how we do it. So what we define here, this is our thin magnetic field. So again, it's also different for different magnetization configuration. We do it only for forward volume waves. I think it's one of the easiest case in terms of how many pages of formulas you need to write. So you have H, it's normal magnetized, pointing like this. This is your sample, and we put our coordinate system in 0. So Z is along the field. Like I said, usually Z is oriented along the field. Y is a direction along which wave propagates, and coordinate is in the middle of film. So it means that D is thickness of the film. So starting from, if our Z is smaller than minus D over 2, then it's 0. So no magnetic field. And when it's above D over 2, then also vacuum. And this is our Walker equation. How we write it? The same Walker equation for 3 regions separately, but for the middle one, it's a proper Walker equation, just copy paste, and here you see this mu permittivity. But when we go to vacuum, here from this side to this side, mu of vacuum will be 1. Therefore, this one is simplified. Moreover, what is simplified here, we forgot about x coordinates. So we analyze now only waves which are running along y, and it means that everything what's going on in the direction perpendicular to it is uniform. Therefore, we just ignore this coordinates, so this part disappears. We keep only y and z component, and mu is equal 1 for this and this part, and it's not 1 for when module of sz is below d over 2, so somewhere in the middle. How to find solution for this equation? We need ansatz, and we of course use ansatz of plane wave. So it means I omega t. So there is some coefficient a which we need to find. I omega t minus ky. It's a wave solution for wave propagating along y direction. And here you say it stays kz, no I. So it means that, and in this case 1, z is negative. So it means that in reality it's minus kz. So it means in such a way we describe a one-essence wave. So if electromagnetic wave, so spin wave, magnetostatic wave propagates in magnetic field, it creates a field outside of the film which exponentially decays. One-essence wave means that it's not real, it cannot propagate there, it's not eigenstate. It just decays exponentially when you go from surface in this direction or from surface in this direction. That's what is shown here for the part 3. It's minus kz. So k modules, it means it cannot change sign. It always decays. Therefore, here we have just decay. And in the middle, it's a real waves. And principally, I can tell you that for these forward volume waves, they're named volume because you can have their distribution inside of volume is given by harmonic function. So it means that you need such ansatz which will give you some harmonic distribution in here. And this one works good, let's say, cosine minus mu kz and sinus minus mu kz. What you have here 4 parameters, A, B, C, and D. And you don't know them, 4 amplitudes. To get them, we need boundary conditions. Boundary conditions, again, it's something you know from quantum mechanics or from electrodynamics, are defined like this. You want to couple that psi 1 is equal to psi 2 at this border, when z is equal minus d over 2, and derivative of d psi 1 over dx, x in that direction, yeah, and d psi 2 over dx also in that direction, and this border should be the same. So you have these 2 equations, and on this border you couple psi 2 and psi 3. So it means that d psi, so psi 2 and psi 3 should be equal here as well as derivatives. And then what do we have? We have 4 equations, 1, 2, 3, 4, and 4 variables, A, B, C, D. Then you plug plug into boundary conditions. You will get bulky formulas, but you can find a solution if you will find the determinant of this system and will make it equal to 0. After you will do this, you will get dispersion curve in such a very not straightforward way. On the left side, there will be tangents of kd square root of mu, and on the right side will be mu, something dependent on mu. And mu is our this complicated formula, and but important is that it depends on omega. Yeah, because our aim here to find dispersion curve. Dispersion curve means we want to have how omega depends on k. And we have omega sitting inside mu from both sides, and we have k sitting here. And that's why you cannot solve this equation further, analytically at least, but it is your dispersion curve already. And what we do in practice we will discuss how to calculate real dispersion curve in real cases with magnetostatic and exchange interaction simultaneously a bit later. But if you want to stick to magnetostatic, usually we use simplified analytical expression like this one, which works perfectly. When I was a PhD student, I plotted for myself this one solution and this one, and they start to I could see the difference already closer to the edge of to the right for large k when principally magnetostatic dipolar approximation doesn't work anymore so good. Therefore, this formula can be used if you want to have quick understanding what is your dispersion curve. And you see it's written in a direct form. It's omega, frequency of forward volume magnetostatic spin waves, as a function of k, of a number. And again, we use omega h, CGS, SI, and we use omega m. CGS-SI. And here it stays D because the dispersion of this curve strongly depends on the thickness of your film. Yeah, to plot this dispersion, we need, first I want to show you a nice animation. So Rostislav, who is sitting here, has made this animation, so that is what means forward volume wave, how it propagates. So this is our thin film, magnetized perpendicular. You have this field B, and you see how wave propagates. So that's a nice animation. And our job is, of course, now to get dispersion for this animation, and it looks like this. So let's take this formula and just send our k to 0. Then what happens in this, if k goes to 0, then this part, so here you have 0, but here also will be 0. But this part, it's, as you know from mathematics, high mathematics, it gives us 1. So it means that this part omega m disappears, and frequency of forward volume wave will be given square root omega h squared, which means simply omega h. So we know where our dispersion starts. K equal infinity, so where it goes when it's very large. Then in this case, this part will be 0 because this one goes to infinity, this one 0. Then we will come to this formula which we know already as omega perpendicular, omega h plus omega m, like it's shown here. Good. Next step, yeah, so we know where it starts from, and let us plot it just as an example. Again, let's stick to YIG in this lecture course. You're already familiar with this material. We take 5 microns of YIG, classical YIG, many experiments are performed on it. 200 millitesla applied magnetic field. And then we have value for omega h, 0.7 gigahertz. We have the value for omega m, 4.9 gigahertz. And we have value for omega perpendicular, it's 195. Yeah, what's important here is that this is 200 millitesla, it's external field. And we should not forget that there is demagnetization according to Kittel formula, which we discussed in the second lecture. So it means that inside of the sample, field will be smaller. It will be only 24 millitesla. In reality, this field is a bit too small. You not necessarily will keep magnetization parallel. It will be tilted closer to the surfaces of your sample. Therefore, in real experiment, I would go for higher fields. But to give you an understanding, that's how we usually do. So it means that you need to take into account this field. That's why omega h frequency is so large, so small. Yeah, and you take usually, if you calculate it, this gamma. If you want to have it quick and easy, you just take gamma over 2 pi 28 gigahertz per Tesla. And then you can immediately plug everything in, and you will see what is dispersion. And that's what we have. Omega h, omega perpendicular. And so 0 is here, so it's not here, but at this point. And you see that it behaves like this. So this is a dispersion curve for forward volume magnetostatic wave, plotted from 0 radian per centimeter. So for this one, I still keep centimeters, just to be consistent with literature. And you see that principally it saturates. So if you go to larger and larger k, unless you take into account exchange interactions, there will be constant. So velocity of magnetostatic wave will be 0 if you go to higher k. But what in reality happens when you go to such higher k, you need to take into account the exchange interaction, which will start to pull it up according to k square law. But for magnetostatic wave, it just saturates here. Other question too? I hope today you simply understand everything that you're not asked. Good. I told you that when we used search for ansatz for solution, we took something harmonical. What does it mean? It means that you can have higher thickness modes. So in the simplest case, if magnetization is distributed over the thickness uniformly, then we usually speak. Sometimes it's always a question how to start count from 1 or 0. But let's say in a lot of typical for literature, this uniform mode is equal 1, is equal 0 when you ignore any magnetization over the thickness of your magnetic field. So it's all uniform here. But you can have here half wavelengths of your magnetization precessions. For example, for pinned case, it would be if you would have no precession at the surfaces. In reality, it's a bit more complicated. Here, spins are usually unpinned. But in the simplest case, to give you a feeling, you can pin them. And then if you have half wavelengths, and this mode is usually named first one, then second, third, and so on. And you have many higher order thickness modes. And if you will go to the very original paper of 1965, Damon and van der Waart, who did it for forward volume waves, these are the dispersions, and this is the lowest mode and equals 0. And then you have such dispersions and 2 and equals 3, 4, 5, and so on for higher order thickness mode. So let's not forget that you can get higher order thickness mode in the system. And that's what you can get by calculating yourself. So here I used Kalinikov-Slavin model, therefore exchange is taken into account. That's why this dispersions you see, it moves above omega perpendicular, because its exchange brings them, but for us this part is important. And that's how it's shown for 0 mode, first, second, third, fourth mode. So that's what you can calculate easily on your own for these particular parameters of yttrium iron garnet film. No questions over there? No? Just don't hesitate to interrupt me. Good. So we have quantization. We have shown how to get from Walker equation to the yes.
I have one question. Can you go back to the slide before?
Yes.
No, the one after. For these higher thickness modes, what does this red?
What red means?
Is this the mode profile?
Yeah, so it's more or less intense. So the question is, what this red means? Thank you, David. It's a very good question. It means amplitude of spin wave or angle of precession. So it means if you have, for example, such case, and if I plot this mode, so it means that this you can consider this one as C, usually just amplitude of spin wave mode, but physically it means that angle of precession, so it's forward volume mode, yeah, so it means that it's perpendicular. Here you will have large angle of precession, and at the edges spins up, so-called pinned, yeah, so it means that there is no precession at all. And here you will have something, some smaller angle of precession. Okay. In reality, as I said, this is maybe not very good example because there is dipolar pinning, and there is even, if you go to lateral dimensions, there is dipolar exchange unpinning, but usually modes for thickness modes, they are unpinned, so they don't have 0 precession angle at the surfaces, but they have maximum precession angle. Then your mode, for example, looks like this, or like this. Yeah, so that you have large angle of precession, particularly at surfaces. Okay.
And in the case M2, because it seems like the amplitude of the precession points in different directions.
It means different phase. It means they are precession in antiphase. And this is a very good point because you cannot excite even modes with uniform field. For example, you want to excite, you put your sample in a uniform field, so you irradiate with electromagnetic field of the same phase. And that means that you excite precession here, here, here with the same phase, and it will work here. Now, if you will go to the second mode, what happens, these two are in antiphase. So it means that if you irradiate it with uniform field, you want to excite this one to precess with one phase, and this one with the opposite. And you kind of trying to pull the sink in one direction and another simultaneously, and then it stays. So it means that you cannot use uniform field to excite even modes in your system, because everything what you're trying to excite from one side will be compensated by everything what you're trying to excite in the opposite side. Therefore, with uniform field, all even modes cannot be excited. But if you go to higher order odd modes, like third, for example, what happens in this case, this area is the same. So it means that again, you're trying to excite this one and this one compensated, but still this one is uncompensated. So it means that with uniform field, when you irradiate your sample, for thickness mode it's hard, but for example, we commonly have it for width mode when you work with waveguide. We still will discuss it later, but you can excite even modes even with uniform field, but the efficiency of excitation drops down So third mode will be excited with less efficiency than first mode.
But antiphase means that the sign is different. One precesses like this and one.
Antiphase means precession. That's the point that we discussed, that Landau-Lifshitz precession direction is always the same, but one side you want it to point in some moment of time. You apply field that it has to stay here, and in another moment and here, this mode means that magnetization should point in opposite direction. Yeah? And then when you want to apply field that you excite, so it's kind of good for this one, it will be very bad for this one, so we'll suppress it. And mode, it means that it's it's one eigenstate, so it fills everything. Oops. So it means that you should have, so you should consider your system the eigenstate over the whole thickness in this case. Thank you for the question. Other more? No? Good.
Maybe this is a stupid question, but experimentally, how do I influence the mode I excite? Like, how can I say, okay, I want to excite the third mode wave? How do I do that?
So the question is how an experiment to excite one or another mode, how to select, how to influence. Usually, what happens in experiment, you just have this mode. So you perform some modes. You usually want to work with the first lowest one. It's the fastest. You see this slope is the fastest, is the best, and so on. You can excite it with highest efficiency, but you start to perform experiment, and suddenly you see that you have many other modes. And then if you will add a bit power, they can also start to interact, and your life is getting very interesting. Therefore, in reality, we are usually searching for a way how to suppress the excitation of a parasitic mode. If you would like to really to excite it, so that's why, for example, we go to nanoscale now structures and nano thickness, because then these modes are getting well separated in frequency because of exchange interaction. We'll discuss it later. And then you can have such situations that you can work with that mode which you want. If you work with this case, magnetostatic, if you want to excite even mode, what you need to do, you need to irradiate, to find a way to irradiate not all your sample, but only half of it. Yeah? So you need to think about some fancy antenna that only half of it will be irradiated. Or ideally with two of them, but with some phase shift of pi. Then you will be able to excite this one. In a real experiment, for example, if you transpond it to width modes, there will be, physics is the same. So here we are discussing thickness, but if you have waveguide, you will get the same quantization over the width. So what is observed in Kaiserslautern that was shown that if you, for example, have such turn in your waveguide, then this inhomogeneity, you see it's not symmetric, it also works very good. So afterwards you will have an equal 2 mode because it's asymmetric and it's not symmetric, this structure. So there are different ways, but a short answer is that usually we are trying to avoid excitation of higher order modes when it's possible. Okay, good. Then let's move on. And we switch to backward volume magnetostatic spin wave. It means that we are now going to in-plane magnetized thin film. And first, our life is getting easier because this is easy plane. So we don't have to apply large magnetic field and we don't have to fight with demagnetization. So field inside of our sample will be the same as when it's applied. And again, here's animation from Rostislav. How our wave propagates, it looks like this. So that's how backward volume wave propagates. Very good wave. In the very first this preliminary lecture, we discussed that it has negative group velocity, but also many other interesting physics behind it. So we often investigate backward volume wave. And again, we don't go from Walker equation. Idea is the same. You need to write properly boundary conditions, Walker equations for 3 parts, and then to couple them. But you can use a simplified analytical solution where you see it's 1 minus, so it's somehow similar but different for this one. And again, when you will analyze this equation, when k goes to 0, then backward volume frequency will go to omega perpendicular, which is FMR, ferromagnetic resonance frequency for thin film when it's magnetized in plane. And when k goes to infinity, then backward volume frequency will be omega h. And it's just opposite to the previous case of forward volume. Forward volume, this was our starting point, this was end point. And now we start with omega perpendicular and finish with omega h. And again, the same example. All is the same except that internal field now is equal to external field. That's why omega h is equal to 5.6 gigahertz. And frequency of our wave is around 8 gigahertz. So much higher frequencies because we don't have demagnetization. And that's the dispersion curve. So we start with omega h, that's 0. And then it goes down to, and then it saturates at this level. Okay. Yes, and again, you have, of course, this higher, again, both volume waves. Volume means that you have harmonic distribution over, so it means that wave is inside, and usually it's harmonic distribution, some sinus cosine. Exactly like forward volume wave, we do have higher order thickness modes, like it's shown there. And their dispersion is, so here just show you that, you see it's exactly mirror, not mirror, so this is not necessarily the same, but this one starts from omega h and goes to omega perpendicular, this one from omega perpendicular to omega h. And here are the higher order modes, and this is a classical paper of Damon-Eshbach 1960, where they described all this magnetostatic wave. Until now, everybody is using this paper, more or less what they... Okay, later people, Kalinikos-Slavin added also exchange interaction, but still this one is one of the most important papers. And they described this dispersion curve, developed all theory. And here are our higher order thickness modes. So n equals 0, 1, 2, 3, 4, 0, 1, 2, 3, 4. So there are again higher widths, higher thickness modes. So there are many modes in the system. Keep that in mind. And again, I use software which uses Kalinikos-Slavin, when again, you see this starts to shift up because of exchange interaction. It's taken into account here. Yeah, so this paper also would be nice. If you want to work with this, just read that. And yeah, as we discussed, what is interesting, one of interesting features about backward volume wave is negative group velocity. So the slope is negative. And as we discussed already, it means that wave propagates in one direction and runs in the opposite direction. And Yeah, so wave runs to the left but carries energy to the right. Yeah, in left-handed media, metamaterials, there is a large field of science, but people are trying to make to get this effect in optical range, yeah, because optical range means you. What is the name of movie Predator? Yeah, with Schwarzenegger. Remember this? Hmm? No, Predator, where he's fighting against Predator, yeah, and that one could become invisible when in first part in jungle they were fighting. Yeah, so if you have material with these properties in optics, it means that your refractive index is negative, and then you can create this cloaking effect when you are in the middle. Let's say that you can be in the middle of some object, I don't know, lens or so. This is you, and light will go then pass like this, and it something like that. Yeah, and then you will be invisible if you would have material with n smaller than 0, and that's what people are trying to do. It, of course, it's of interest for military, but this kind of things exist in electromagnetic business. There is a use complicated systems with many different resonators and very complicated dispersion curves. You can get it for electromagnetic wave, and for spin wave we have it simply because of dipole-dipole interaction, more or less for free. And this very important graph, again from the same Damon-Eshbach paper, which shows us how dispersion curve looks when spin wave propagates not only parallel to the applied field like it was before, but under some angle. Because we usually, to make our life easier, we consider this case, and this case. Yeah? And in reality, all others are possible, and that's what is going. So what we discussed in the previous slides, this thing is just cross cut of this 3D graph along this axis. So these are our dispersion for lowest mode and higher thickness mode. But when you go to higher and higher, to change angle, this one is a wave which propagates perpendicular to the magnetization field. And you see that very important that people sometimes say that there is no backward volume wave with K perpendicular to field. No, it's not the case. This dashed line, this is dispersion curve for this perpendicular wave. The only issue is that it doesn't propagate. You see, it's flat dispersion, it has 0 group velocity. But wave is still in there, and we will discuss when we will talk about perpendicular standing spin wave, that this is very important. But for any angle you want to have, you have dispersion curve. But it will become more and more flat, so it means that velocity of wave will be slower and slower when you go away from the ideal magnetization along. So at this point I will stop. Other questions to today's lecture? Yes, Rostislav?
Yes, in this graph, I think you can see that the Damon-Eshbach mode, the magnetostatic surface spin wave, is with group velocity 0 at 45 degrees.
It's not 45 degrees, but you're absolutely right. We will discuss it in the Damon-Eshbach part. This is a Damon-Eshbach, and it also exists for other angles, but not for all angles. So this is cut-off frequencies, cut-off angle. So if you go above this phi s, there is no Damon-Eshbach. That's what we need to keep in mind. And you're absolutely right that here velocity changes and also bandwidth in which it exists changes. But this is not 45 degrees, it depends on omega h on magnetic field. So you can tune it. And I just recently have found a nice paper where people made, Professor Zavislak made the RF filter based on magnetostatic wave, and they tune the bandwidth of your filter simply by changing angle for Damon-Eshbach. So, and it's a really cool result. Yeah. Other more questions? If it's, yes?
Yes, and the question to the previous slides, and we calculated or like set the boundary conditions for our thickness. There was the derivation to the x.
Yes.
Component.
Yes, you're right.
Like just a simple question, like in the formulas above for the amplitude of the wave, where would be this x that would be derived? To which we derive? Is it in the k, like in the wave vector, or?
So the question is, when we take derivative from x, where it is here. So my answer would be maybe mu is a tensor, so it should depend on all parameters, all three coordinates. I would say that it should be in the mu, but let me double check and we'll discuss next time to make sure that.
Then the question again is k in the exponent vector or the way it comes? Like there you have k as x, y, and z?
No, here we already have it.
You have like you have a wave number where k is like the absolute value, and then we have k as not the absolute value. Is it then the vector is something different?
So I assume we already simplified. So we work only with the projection of k towards y, and we ignore all other k's. So.
No, why do we have like then the absolute value of k in the exponent, and with like before that we have the absolute value? Yeah, and after in the imaginary part we have it without.
And the imaginary, this one without. Yeah, so here I just place it because k can propagate in one and other direction. And it means that if wave runs along y, it's positive. If it runs in the opposite direction, it's negative, which in this case are identical keys. But then mathematically, if you would plug in here negative k, or here negative k, yeah, it means that you would get positive exponenta. So it means that your field from the surface would not decrease like a evanescence wave, but would amplify. And then it's unphysical. Therefore, just to make it impossible, we place it here. But for plane waves, then of course it can run in one or other direction. It's okay. So good morning, everyone. Today we continue our lecture. Our job is to finish magnetostatic spin waves. And our next type, the last type of spin waves, is named magnetostatic surface spin wave or Damon-Eshbach mode, because Damon-Eshbach have published them for the first time and describes their properties. As I said, the spin in brackets because all terminology would be magnetostatic surface wave, MSSW, and new way, how we name it, it's magnetostatic surface spin wave. Yeah, so just don't be mixed up, but you will understand what we are talking about. And now we're discussing in-plane magnetized thin film, like for backward volume case, but wave is running not along the applied field, but perpendicular to it. So here we see this animation, how our wave Damon-Eshbach mode or magnetostatic surface spin wave propagates. Again, like in previous case, there is a simplified analytical solution for this wave. And what is very important for this wave is that it is a surface wave. So it means that if previously these waves were named volume, it means that they exist over the whole volume, and the distribution over the volume is given by harmonic functions, so sinus or cosine. Now we are speaking about surface wave, so it tries to propagate over the surface. And it means that it suppresses its magnetization, its amplitude to one of the surfaces, like it's shown here with different colors. So with next slide, I will show you why they suppress for different sides. But principally, you should understand that now distribution of magnetization inside of the film is given by the exponential function with maximum at the surface, and then it decreases exponentially in the volume. Let us analyze the dispersion curves. Again, we do it simply from this analytical formula. If k equal to 0, then omega magnetostatic surface spin wave is equal to omega perpendicular, which we know very well. And this is correct because this is ferromagnetic resonance frequency for in-plane magnetized film. Yeah. So what means ferromagnetic resonance? It means that phase, that k is equal 0. So it means that wavelengths, you can see it as a spin wave with infinitely large wavelengths. It means that if you take our sample and infinitely large wavelengths, k equals 0, means that all spins are precession in phase in the whole sample. And in this case, there is no difference if you look. So if your magnetization from this direction, yeah, there is no difference when you analyze sample along this direction or along this. They're all precession in phase. Therefore, ferromagnetic resonance frequency should be the same for in-plane magnetized, independently if we are speaking about backward volume or Damon-Eshbach. Therefore, it's logical that for k equals 0, we obtain the same frequency as it was for backward volume. But things changes when you start to change k. Because in this case, from this analytics, you can get a formula for spin wave, and this frequency for this limiting case will be omega h plus omega m over 2. And this value is already larger than omega perpendicular. Example, again, our X of this you have seen for backward volume, that's frequency omega h 5.6. The 7.7 gigahertz we had already, and omega h plus omega m over 2 is equal a bit more than 8 gigahertz. So it means that now frequency of wave increases with increase in k. Okay, let us have a look on the dispersion. So here how it looks like for the same k maximum. Therefore, I especially keep the same scale that you see that it's very steep. So it means the Damon-Eshbach is faster principally than backward volume. You can see it in the simplest case. And so we have here some small it deviates from this horizontal line. It's a line. It's again we will discuss a bit later. It's because more complicated model is used here, but principally magnetostatic wave should go just to be constant here at this level. And very important, since it's exponential decay, there are no higher order thickness modes. So Damon-Eshbach does not quantize itself over the thickness. So it means that there is only one curve, dispersion curve, as opposite to backward volume, where we had many of them. Yeah, and that's how it looks like. This is our FMR frequency. Then if you increase k along the field, it goes down backward volume. And if you wave propagates perpendicular to the field, then it follows this MSSW dispersion curve. Okay, now let us come back to this point. So dispersion, you see what is drawn here is that wave which propagates into one direction, this green one suppresses its magnetization to the top surface of the film. Wave which propagates in the opposite direction runs over the other surface of the film. And here it's shown in this animation. That's how it, if you have antenna on top of the film, then it propagates towards the left. Yeah? If you would take the same picture and would just turn it upside down, you would see that antenna stays here and wave runs in the opposite direction. Yeah? So here it runs like this and like this. But since in practice, usually below your waveguide there is a GGG substrate, and it's very hard to put antenna under GGG. What we do, we just change magnetization direction. So you see here all these arrows are pointing to us, and here we just turn them to other direction. It's the same if you would change magnetization. It's the same if you would go from one side of the film to another. And when we stay here, then it propagates in the opposite direction. You see, so this one runs to the left and this one to the right. So really, it suppresses its magnetization. But what we need to keep in mind is that this distribution over the thickness the simplest case can be given as exponenta minus kxy. It means that, so it's distribution along y, but here is tan kx. It's a k of wave propagating in plane, yeah, so which is running here. And usually for practical purposes, since our thickness defines maximum y, so it's quite small value, and k can be usually larger, what we have that this exponenta, even for the largest y, which is equal thickness, very close to 1. Therefore, what we have is that in reality, we not so often see such a strong distribution. We will have something more, let's say 100% here and 98% on the other side of the field. Therefore, please be careful that there is this non-uniform distribution, but not as strong as in this animation. Yeah, when we have large precession here and small precession angle in this case. It's not so easy to get, so let's say you need very thick sample for this. Therefore, keep this in mind that there is spin wave is where this Damon-Eshbach is non-reciprocal. Non-reciprocal is a term means that wave which propagates in one direction is different than wave propagates in the opposite direction. What means different? It can have different dispersion, different frequency, different group velocity. It can be different amplitude and something else. So Damon-Eshbach is the only wave which is really non-reciprocal. Another important point, if to make comparison between different waves, there is also anisotropy. Yeah? So we have seen clearly that with this curve, that these waves for in-plane magnetized, they are anisotropic. So wave propagating in one direction for backward volume is different than wave propagating in the opposite direction. For Damon-Eshbach also, wave propagating perpendicular to field will be different, that wave runs under some different angle, and it's very different when it runs perpendicular. So in principle, there is no Damon-Eshbach which propagates along the field. Therefore, keep in mind for in-plane magnetized samples, our spin waves are always anisotropic, except one case. Which case where we have isotropic spin waves? Forward volume, yes. Because in forward volume, we have magnetization perpendicular to plane, and it means when wave runs, MS is always perpendicular. Therefore, it's isotropic. And if you want to perform experiment and to come closer to optics, for example, to work with a nice wave, then we go to forward volume. If you want to have fancy, complicated physics, then we go, or if there's any other reason, we go to in-plane. Okay. And forward volume and backward volume, they are reciprocal. So wave which propagates in one direction is exactly the same as wave propagating in the opposite direction. So these are reciprocal, but not MSSW. MSSW is non-reciprocal. So I said that although it is non-reciprocal, this field distribution is practically uniform here. But if you will perform such an experiment, so this is experimental study done in Kaiserslautern in the group of Burkhardt-Hillebrands, and here Thomas Schneider has performed measurements under the direct supervision of Alexander Sirha, and Mikhail Kostelev have written a theory to explain this interesting phenomena. So what you see here is a simple microstrip antenna, and they send a pulse, microwave pulse, to excite spin waves. And they detect spin wave with brilliant light scattering spectroscopy. It's a topic for our further studies. We will discuss later how this technique works, but it's just a fantastic technique which has time and space resolution. And you can plot movie how this pulse really propagates. So here they took just one frame, one time point when it's already excited. And they performed the same. So it's macroscopic YIG. I don't know, 5 micron thick or so, like 2 millimeter wide, 2 centimeter long, something like this, typical sizes. And they compare two situations. If you excite backward volume, which is reciprocal wave, you see that pulse is propagated, identical pulse is propagating in both directions. So your antenna excites waves which run in the same way to both directions. If you now do the same with MSSW, with Damon-Eshbach, antenna will excite only a spin wave which runs only in one direction and not to the other. Yeah, and the first what comes into head, of course, is because of this one. Yeah, we have antenna, we have large amplitude, we apply field here locally, therefore wave runs, and this one simply field of antenna is far away, we cannot excite it. It's not the case because it's uniform. Here there is another mechanism, that's why I want to add it, mention it in this lecture. Also, Vlad Demidov and Sergei Demokritov, they have shown similar effect for nanoscale. It also hit there at microscale, but with larger efficiency in paper afterwards. But what is shown in this paper, principally the message is that the reason behind this non-reciprocity is in the excitation, not in the properties of wave itself, but how antenna works. So when your antenna works, it creates such a field. Here there are two components, one and another component, so perpendicular in plane. So principally for backward volume, only this in-plane component, or this in-plane component doesn't work because it points along the field, and only these two are working. Damon-Eshbach excitation is more efficient because this component works in plane, it's perpendicular to the applied field, and up and down components work. They're also perpendicular to the biasing field, so all three components are important. And what else they have measured and described theoretically, the phase. The point is that when you excite backward volume wave, there will be a wave which propagates in opposite direction, will have excitation, will have different phase. So this one has opposite phase, shift by pi, compared to this one. And in Damon-Eshbach, the phase of excited waves to one and another direction will be different. So principally, how to give you the finger kind of explanation, it means that all this complicated excitation mechanism here will be in phase for a wave propagating in one direction, and it will be in antiphase for wave propagating in the opposite direction. Therefore, we have such situations that Damon-Eshbach is really, in such simplest case, is excited preferably in one direction. So in your experiment, always check when you measure S21 parameter, check also S12 because it might be much larger. Questions to general idea, just, yeah.
How is the phase measured in the experiment?
So in BLS, you can add phase resolved BLS. So it means that you send light, it interacts with magnon and scatters with some phase. Phases of light is given by the phase of magnons. Then what you need to do, before you send this laser to your sample, you split it into two parts. You send it through a so-called electro-optical. There are different ways how you do it. You need to get part of this light to have detuned frequency, the same as frequency of spin wave. So you apply 7 gigahertz, and then this reference light you send through electro-optical modulator, you will get 7 gigahertz shifted frequency. And then you merge this one reference, this shifted by device and its constant phase, and you merge light reflected from spin waves, which carries another phase. And then you just merge these two light together and send it to interferometer. If magnon had the same light phase as your reference, then the same signal will be twice larger. If magnons changed phase by pi in some concrete point, then this reference and your magnon signal will be in antiphase and amplitude of light will be 0. And then it means that you, after interferometer, you will see amplitude of modulation of amplitude 0 to maximum, and it gives you phase of spin wave since reference is constant. Yeah. Good. Yes.
The fact that in the magnetostatic surface modes, the spin waves are propagating only in one direction is only seen with strip line antennas, right? So with coupling waveguide, it's not.
Oh, I would assume it's still there.
In the both directions are different.
You see, CPV does not. It's not so different compared to strip line. Yeah, so in CPV you have also coplanar waveguide. You have also middle line which will create similar field, but there will be two other lines on the sides with an inverted field. Yeah. I would guess that CPV also will give you a non-reciprocal excitation, so maybe even more pronounced than strip line. But I never performed it. I never checked how it's really working. Yes, please.
So, but it's not only the excitation efficiency of antenna; it's also the geometrical restrictions because of the reciprocity of the spin wave. because the spin wave comes in one direction on one surface, in another direction on a different surface, right?
Yes, it might be, but in terms of phase. No, so Andreas asked if it also relates, it's not only antenna, but antenna and property of spin wave. Might be, but not because of amplitude distribution. So amplitude distribution is uniform, but phase is different. So maybe antenna, this recomponent of antenna field with different phases, and the fact that this has another phase as this one, altogether probably gives you what you say, what we see. Good. Okay. Now one more point, again from a very practical perspective. Till now we considered and we solved Walker equation in the case when there is nothing, there is air on top. So principally we considered free film, and there is magnetic film, and there is vacuum or air. But of course you can put here another magnetic film, or you can put metal. And what happens if you metallize your film? For example, yttrium iron garnet, it's hard to metallize it from bottom because usually it's growing on gadolinium garnet, gadolinium garnet substrate. But on top you can metallize it. And then you need, of course, to change boundary conditions for your Walker equation and to solve everything from the beginning. But it will give you the following situation, that in the case of free non-metallized thin film, the dispersion, you can use this simplified equation, and we have this two dispersions when it starts and when it finishes. When you have metallized thin film and you study Damon-Eshbach, you see that this changed, and here you can use this dispersion curve. And in this dispersion curve, the beginning of dispersion is the same, but at the end, k equal infinity, omega h plus omega m stays here. So it's another frequency. How does it look in reality? I didn't plot here dispersions, but if you will look on this dispersion, for example, so here you should add omega h plus omega m somewhere there, and it goes like that. And this dispersion, and principally metallization for Damon-Eshbach works very good, because it does not change damping, it really just increases width, spectral width, where you can work with spin wave because of higher frequency, and moreover it makes dispersion steeper. So it means that spin wave, Damon-Eshbach, is getting faster in metallized samples. Therefore, metallization is quite good for Damon-Eshbach, but you still have to take into account how you apply antenna, where you put metallization, because if you have antenna, free sample, and then metallized starting from some point, when wave is running to this metallization point, it has to change its dispersion. Yeah? So it had one dispersion in the free path, and dispersion for metallization, another one. So it means for the given frequency, it should make a jump in K. And then it might make jump in K, or it might reflect. Then you need to analyze situation, but principally expect always reflections from metallization. If to speak about metallization for in-plane magnet, for backward volume or forward volume, then it doesn't change. So in Gurevich-Melkov you can see dispersions for metallized samples. It doesn't change dispersion so dramatically, but there will be parasitic reflection, and the potential might be additional mechanisms for damping. So principally in backward volume, when you will do the same, when you take simple waveguide to antennas and you measure Damon-Eshbach, you put metal inside, you will see that transmission improved because the waves are getting faster and broader spectrum. If you do the same for backward volume, you will see that transmission is much worse. So probably metallization induces also additional damping mechanisms. And therefore be careful with metallization depending with which waves you are working. Now let us see on the parameters. As I said, if you compare magnonics with photonics, for example, which is much bigger, much more powerful field, We see light, yeah, it's clear that light is very important. But if you build a device, then usually you have only one parameter which you tune. It's refractive index n. Spin waves have advantage that we have more parameters which you can tune in order to change properties. Field applied or sit in omega h, material of different magnetization sits here in omega m, and principally thickness of the film d. And let us have a look how you can play with parameters in order to tune your wave. For example, here shown the same dispersion for Damon-Eshbach mode and for different fields, 200 millitesla and 250. And you see that what happens, it shifts a bit up, like it's shown here. And then why it shifts? So principally, this a final frequency is omega m plus omega h over 2. So principally, this delta is linearly proportional. Shift of this curve is not straightforward. It's omega perpendicular, which is a bit more complicated, yeah, because here it's omega m. But still, it's close to linear, especially if omega h is much larger than omega m. Therefore, this shift up will happen with small compression of spectrum, but not very big. The main effect which you see is really shift of dispersion up or down, like it's shown here. And it means that in our experiments, we can really just shift everything. So you can principally define any k you want to work with, and you can define frequency at which you want to have wave simply by the applied magnetic field. Good. We can change field. Second, thickness. Thickness. Here we have again the same dispersion, again Damon-Eshbach, but just two different thicknesses. But here I don't show it to the very large k. So principally the saturation level for dispersion will be the same, but it will happen somewhere far away. I zoom in this beginning of the dispersion curve, and you see that slope for the curve of 5 micron is larger for 5 micron and is smaller for 1 micron. So it means that velocity of magnetostatic surface spin waves or all magnetostatic waves strongly depends on thickness. How depends? Again, a bit more complicated characteristic, but if you will consider some part of spectrum, and we'll say that here the change is linear, principally, then this behavior is linear. So it means that velocity is proportional to the thickness d. How to memorize this thing? Usually we say students such an example that imagines that you have autobahn, so some highway with 2 lines, and cars won't be able to move very fast. But if you have highway with 5 lines, cars will go much faster. So somehow similar, of course, finger explanation, but for memorization it's good. So in SIG sample, waves are much faster than in SIN. And this gives us additional opportunity, so we can tune k and omega by frequency, by applied field. And on top, we can also say that I want to have wave with this k and this frequency, but of such a given velocity. So we have a possibility to tune third parameter velocity independently, and this gives a lot of advantages for different kind of special experiments. And last parameter which we have in this equation is magnetization, MS. And here I show you just 2 different materials. One is yttrium iron garnet, and another very popular material is permalloy. It's alloy, nickel 81, iron 19. And it has much larger magnetization. And you see that for the same applied magnetic field of 200 millitesla, a frequency for permalloy is much higher. So for YIG, we would work with frequency spin waves around 8 gigahertz, and in permalloy, it would be around 15 gigahertz. So you can, by changing material, you can shift the frequencies up and down. Of course, in reality, you also need to take into account anisotropy, for example, hexaferrites. Then it's a material where M is not so big, but there is a big, like barium hexaferrites, big anisotropy induced. And then you can define so-called M effective, where anisotropy is sitting inside, and of course then you can go to 60 gigahertz frequency simply by changing material and still applying small field. If you want to go to work with YIG, but at 60 gigahertz, you need to apply very big field. Also possible, but you need to think how to get where to get a large field for YIG. And very last slide. Here, this picture you have seen already when we discussed backward volume. There are higher thickness modes for Damon-Eshbach for magnetostatic surface waves. There are no higher modes, and the backward volume exists in the whole. For all angles, Damon-Eshbach exists only in some range of angles, from 90 degrees when field is wave is running perpendicular to the applied field, up to some critical angle phi s, which you can find as tangents minus 1 square root of omega h. Omega h is principally our omega h, which you have, so it depends on the field. So it means that keep in mind that Damon-Eshbach can run, so if this is field, it can run in some range, but only in a given one, and you can control this cutoff. By the way, I have seen one paper where people developed a RF filter using spin wave, Professor Zavislak, and he tuned the bandwidth of the filter simply by changing orientation of magnetic field. So if it's perpendicular, then bandwidth was very broad, and when he was turning the field, he could nicely tune it and could get any bandwidth because, so then you just work with another in another range of frequencies. Good. So much about Damon-Eshbach. Other questions? No. Good. I hope I could give you an overview, what is important, what is special about each type of wave. But as Simon asked, all this was about plane infinite film. And now we need to switch to real sample, which is usually a waveguide.